All right, so the last thing we need to talk about with instrumental variables is we need to talk about this idea of compliance and what kind of effects we're actually measuring in our population, and the limitations that imposes on our causal effects that we find when we run these types of regressions here. So to do this, we need to go back to this whole idea of the potential outcomes framework. We've been talking about this throughout the semester, where if you want to find the causal effect of a program, that little d delta over there, you want to find the value of y, which is our outcome, when the program is yes, minus the value of y when the program is no. And that's how we find if something has an effect. And so there's our causal effect of the program. P is the program, y is the outcome. And so this is what we want to find, is the effect of a program when it exists minus when it doesn't exist or when it's not used. The problem with doing this at an individual level, again, we've talked about this a lot, is that you can't. This is the fundamental problem of causal inference. You cannot see individual level effects of a program because you cannot observe what would happen to somebody if the program is yes and subtract that from what would happen if that person didn't use the program. This equation right here with the I subscript is impossible at an individual level. We can't do that. So how do we get around that? We've been talking about this throughout the semester. You use average treatment effects instead of individual treatment effects. And so with average treatment effects, what you do is you find kind of the average expected value when a program is on and subtract it from the average value when the program is off. And so instead of looking at just individuals, you say all the individuals when the program is yes, find out their outcome and subtract that from all the individuals who were not in the program and find the outcome there. And theoretically, whatever average treatment effect you find, that is for the entire population. And so this is the simpler way of writing it here, where the causal effect, that little d, is the average outcome when the program is yes minus the average outcome when the program is no. And that applies to the entire population. So every individual has some sort of causal effect that we can't see. The average treatment effect is the average of all of those unit level causal effects. If we're just adding everybody's causal effect together. And so we can say that it is the effect for the entire population on average. And so researchers like to find average treatment effects because you can say this policy or this program that we're using has an effect on all of society, and this is how big it is. And so we like finding average treatment effects. We've talked about other causal effects that you can find back in earlier parts of the semester, where you can find the average treatment on the treated effect. And so you're just looking at the effect of the program on those who got the program. You can also find conditional average treatment effects, or CACE. And this is just dividing your population into subgroups. And so you can find the conditional average treatment effect for males and females, or for students and faculty, or for however you want to split up your data. You can find specific conditional average treatment effects or treatment effects for specific subgroups of your population. Also, when you're looking at these subgroups, the effects might be different. And we've talked about this with regression discontinuity. When you find the causal effect in regression discontinuity, you're not finding the total average treatment effect. You're finding something called the local average treatment effect. And so in regression discontinuity, you're only finding the effect of the program for people in this bandwidth here. So you're throwing away all this other data. You can't really talk about the treatment effect of the program on these people or on these people. They're out of your causal inference window. You're only looking at these people. You can expand the bandwidth like you do over here, but then that changes how big or small your treatment effect is. And so what you're left with is just the local average treatment effect. It's not for the whole population. Last time we talked about the fact that you can't make population level claims with local average treatment effects. You can't say that a specific program makes the whole population increase their wages by X amount on average. You can only talk about the bandwidth. But we did talk last time about how that's okay in the end. And we found that quote from Engers and Pischke that said that pretty much all average treatment effects that apply to an entire population only really apply to a segment of the population, even if we call them a population level average treatment effect. Even like a randomized controlled trial ostensibly has an average treatment effect for a whole population, but they're generally limited to a sliver of society, just a few villages, just a few municipalities if you're doing some sort of statewide policy. And so if you don't have good, strong generalizability, all of your effects are just local anyway, or some conditional on something. And so there's no, like, finding a true, perfect average treatment effect for the whole world is impossible. And so it's fine to make claims using local average treatment effects or conditional treatment effects for a population, for a segment of the population, as long as you make that clear and kind of emphasize those caveats. So in regression discontinuity, the local average treatment effect is the people in the bandwidth, so that's all you're looking at. With instrumental variables and randomized controlled trials and other things, your local average treatment effect are the compliers. We're only looking at the effect of the program on people who are assigned to the program and who then do the program. We're not looking at other parts of the population. We're just looking at the complier causal effect. So what does this compliance stuff mean? So to introduce this, I'm going to talk about 4 types of people that you might come across in a randomized controlled trial or in the world in general. You have compliers who are assigned to a treatment group and then do the treatment, or who are assigned to the control group and don't do the treatment. So they obey. They do what they were supposed to do in the trial. They were assigned to be treated. They do it. They were assigned to not be treated. They don't do it. So those are compliers. You have always takers who will always do the treatment regardless of assignment. So if they are assigned to be in the treatment group, they'll do the treatment. If they're assigned to be in the control group, they'll find a way to do the treatment still. And so those are your always takers. Your never takers are the opposite. They will not do the treatment regardless of what they were assigned to. And so if they were assigned to be in the treatment group, they won't do it. If they were assigned to be in the control group, they won't do it. The last group are called defiers. And these people basically do the opposite of what they were assigned to do. So if they were assigned to be in the control group, they'll do the treatment. If they were assigned to be in the treatment group, they won't do it. They do the opposite. So these are kind of the 4 general categories of people in the world when you're talking about assignment to experiments or assignment to natural experiments in the case of instrumental variables. So what we can do to illustrate this and why it's tricky and what we're actually measuring with instrumental variables and other things is we can look at this with this fake data set we have here using these hypothetical people. And this is based on data that we can say that we observe. And so if you look at the legend up at the top, each of these rows is a person. And there are 2 squares. The square on the left is for what they would do if they were assigned to treatment, and the square on the right is what they would do if they were assigned to the control group. And because this is all hypothetical data, these are what would happen if we had a time machine. We could see that first column. If they were assigned to treatment, they would do it. If they were assigned to control, they would do it. And so it's Y and Y. And so that first group of people, those are always takers. They will always do the treatment regardless of how they're assigned. This middle column here, these are the never takers. If they're assigned to treatment, they won't do it. If they're assigned to control, they also won't do it. This last column are the compliers, where if they're assigned to treatment, they'll do it. If they're assigned to control, they won't do it. And so these are their potential choices here. And we can observe both of their choices because we have a time machine and we can read their minds. If you notice, there's one group here that I left out. There's no column of defiers. If we did have the defiers, this would be switched. This would be a no, and this would be a yes. But to simplify life, what economists do is they generally assume that defiers don't exist. Or if they do exist, that they don't really matter in the analysis. And there's a few good reasons for this. In drug trials, it's hard to be a defier. You can't get access to the medicine without being in the treatment group. And so if you want to defy, that would mean that you would be you'd be assigned to treatment and then not take it. Or if you're the defier assigned to control, that means you somehow have to get the medicine to then take. And so if you're a defier assigned to control, you can't really get the medicine to defy. And so it doesn't work. In development contexts, it's similar. If you had like a randomized control trial for bed nets, a defier who was assigned to treatment would have to tear down all of their mosquito protection in their house out of spite. And that's how they would defy the assignment to treatment, which again, like that's weird. That probably doesn't happen in real life. And so we can ignore defiers because the situations where you would defy being assigned to treatment and control are kind of illogical and odd. The official term for ignoring defiers is this idea of monotonicity, the assumption of monotonicity. It's a fancy word that just means the being assigned to a treatment only has an effect in one direction. And so being assigned to treatment can only increase your chance of being treated. So if you're assigned to treatment in a drug trial, that's going to boost your probability of getting the drug. Being assigned to treatment in a drug trial is not going to reduce your ability to get access to the drug. If you're a defier, it would move your probability of treatment to 0 because you're not going to do it, you're going to defy. But we're just going to assume that if you get assigned to it, you're going to do it. Or you're going to potentially do it. Your chance of doing it increases. And so we can ignore the defiers because of this monotonicity assumption. It also simplifies all of the weird algebra that we have to go through to find our causal effects. So let's look at this. So on this slide here at the top, we have our population just as kind of a reference of what these people look like in a potential outcomes world where we can see both of their decisions. So again, the left side means what they do under treatment. The right side means what they do under control. And so we have a population of always takers, we have a population of never takers, and we have compliers. And we randomly assign them to treatment and control groups here. But because we don't have time machines, we can't read their minds, we don't know what these people do. So if you look at this assigned to control group, these people did it. They did the treatment even though they were assigned to control. If we look at assigned to treatment, that first row, those two people, they did the treatment because they were assigned to it, and so they obeyed. And then the second row here, they did not do the treatment even though they were assigned to it. So our goal here, we want to find the effect of this treatment on just the compliers. So what we need to do is be able to see, we need to figure out who of these people are compliers and just look at them. The tricky part though is it's hard to figure out who the compliers are. So if we look over at assigned to treatment, those two yes people could potentially be always takers because under the treatment condition, they will take. So if you look here, they could be these people here. It could also be the compliers. We can't tell. So that group right there are the always takers and the compliers. This group here, who they were assigned to treatment and they didn't do it, if we look in our population, these are the never takers. And we know that for sure. None of these are always takers or compliers. We know that these are just the never takers. If we look over here at the assigned to control world, these people who were assigned to control and still did it, those are not the compliers and they're not the never takers. They have to be just the always takers. So it's just that segment of the population. These people here, though, that were assigned to control and didn't do it, some of them didn't do it because they're never takers and they wouldn't have done it anyway. And some of them didn't do it because they were obedient and they complied. And so here we have our never takers and our compliers. The tricky part here, though, is if we want to know the effect of this treatment, the effect of this program on the compliers, they're bundled up here with the never takers, and they're bundled up here with the always takers. There's no easy way to extract just the compliers because they're kind of linked in with the always takers or with the never takers. And that's where it's tricky to be able to pull apart the effect of the treatment on compliers. But we can do it with some mathematical trickery here. So to do this, we'll introduce one more causal effect, kind of like the treatment on the treated effect. This is called the intent to treat effect. So this is the effect of being assigned to the treatment, but it's not the actual treatment. It doesn't matter if you did it or not. It's just the effect of were you assigned to the treatment group. So if we look down here, back to our observed world, we see some people doing it, some people not, some people doing it, some people not. The intent to treat effect is the average causal effect for the people in this orange box here. All of those people combined, we find the causal effect of being assigned to treatment compared to assigned to control. And that is our intent to treat effect. And that you can measure. You just figure out the average value of people assigned to treatment, subtract that from the average value of assigned to control. There's your intent to treat effect. The last causal effect that we care about is this thing called the complier average causal effect. That's the thing we care about the most. That's the local average treatment effect for just the compliers. So if we look here, it is what is inside this tiny box here. We want the effect of just the compliers who were assigned to treatment, just them. But as I mentioned before, extracting these guys is really hard to do because they're lumped in with the always takers. But then if we decide, let's look at the control group, maybe we can find the compliers there, they're lumped in with the never takers here. And so we can't figure out how to extract that. Ideally, we'd want to. That would be great. So back to our world here, we have our always takers and compliers. We have our never takers and compliers. Our intent to treat effect is this right here, the effect of just being assigned to treatment. But we can do some mathematical trickery to figure out what proportion of compliers there are in our data set. And the reason we can do this is because of this intent to treat effect. So this intent to treat effect, again, is just the average value of this minus the average value of control. But you can break that down into these different groups. And so if you look at this formula here, we have pi, which again does not mean 3.14. This is just because econometricians like to use pi for proportion because it starts with a p, but it is not a p. So that's all the pi sign here means, is it's not, again, it's not 3.14, it's just the proportion of compliers. And then the proportion of always takers and the proportion of never takers. And so the one way to calculate this intent to treat effect is if we say there are 33% compliers, we figure out the treatment and control effect, or the average treatment, or the average outcome for people in the treatment minus the average outcome for people in control for just the compliers. If we add that to the always takers effect and add that to the never takers effect, we add all of those up and that gives us the intent to treat effect. So it's really just kind of the weighted average of all of these different effects for compliers, always takers, and never takers. Okay? So we can also write this as kind of this abbreviation here, where we have the complier average causal effect, the CACE. We have the always taker average causal effect, and we have the never taker average causal effect. So if we can find all three of those, add them up together, that turns into our intent to treat effect. And the reason that's important is we can start using algebra to find this complier average causal effect. So here's the math formula we want. We want to know the proportion of compliers so that we can then find the complier average causal effect. We also have to know the proportion of always takers and the proportion of never takers. We can't measure that though. We don't know how many compliers there are. We don't know how many always takers there are. And we don't know how many never takers there are. But what we can do is, using some mathematical hand waving here, we can assume that the always taker effect and the never taker effect is 0. And the reason we can assume that is that we can assume that the distribution of compliers and always takers and never takers is essentially random. If we have a good exclusive instrument, then being assigned to a treatment doesn't make you more likely to be an average or an always taker or a never taker or a complier. You just exist the way you are, and we can assume that that's kind of randomly distributed. And because it's randomly distributed, that total effect is basically 0. And so what that lets us do is the actual effect of the program on always takers is kind of, we wave it away. And the effect of the program on never takers, we can also kind of wave away because of this assumption of randomization throughout society. Which means if we multiply 0 by the proportion of always takers and 0 by the proportion of never takers, those disappear. So what we're left with is our intent to treat effect is the proportion of compliers in society, which we have no idea what that is, times whatever the complier average causal effect is, the CACE there. Okay? If we're most interested in finding this complier average causal effect, that's the main causal effect we care about when we're doing instrumental variables or regression or randomized control trials or any of these things. We only want to see the effect of the program on people who did the program. We want to get that CACE all by itself. And that's the thing we care about. And so we can use algebra. If we divide both sides by this proportion of compliers, what we're left with is the complier average causal effect is the intent to treat effect divided by the proportion of compliers in society. So if we can somehow find the intent to treat effect, which we can, because that's just the average of people who were assigned the treatment minus the average of people who were assigned the control. And if we can somehow find the proportion of compliers, if we can divide those two, then we get our complier average causal effect. So this is the magic formula that we care about here. We want to find the intent to treat effect, and we want to find the proportion of compliers. Intent to treat effect, we've got already. We just find the average outcome for treatment minus the average outcome for control. Finding proportion of compliers is a little bit trickier though, because again, they're lumped in with the never takers and the always takers. So we saw this before. Now I rewrote this with pi instead of always takers and compliers, but that's basically what we have here. We have the proportion of always takers plus the proportion of compliers, and we have the proportion of never takers. So what we want to do is we can somehow figure out this proportion of compliers. We need to figure out what that actual number is somehow. So if we look at this math equation here, we have this proportion of always takers plus the proportion of compliers. That is something that we can measure in our data set. It's the proportion of people who were assigned to treatment and did the treatment. So we have that proportion there. That's good. We can use some algebra to move this proportion of always takers to the other side of the equation so that we're left with just the proportion of compliers. So if we move that over here, what we're left with is proportion of compliers is whoever was in the treatment and did it minus the proportion of always takers. Who is this proportion? How do we figure out this proportion of always takers? If we look back at our tables here, do we have any of these groups that are just the proportion of always takers that aren't in, so here we have never takers plus compliers. That's all combined. We can't really extract that very well. But if we look here, we do have the proportion of always takers. We know what that is. It's the people who were assigned to control and still did the treatment. So we do have proportion of always takers all by itself. We can figure that out in our data, which means this proportion of compliers we can figure it out from our data. It's the proportion of people who did the treatment, who are in the treatment group, minus the proportion of people who did the treatment, who are in the control group. So as long as we have both of these, the intent to treat, which is average of treatment minus average of control, if we divide that by the proportion of compliers, which we can figure out given our data, then in the end, we can actually calculate the complier average causal effect. We just take intent to treat, divide it by the proportion of compliers, and that is our local average treatment effect, or our complier average treatment effect, average causal effect. The magic thing about all of this is, again, it's faster to do with this two-stage least squares regression stuff. Because as I've mentioned throughout this lecture, any of the causal effects that you're finding with instrumental variables is the treatment effect for just the compliers, which means it's the complier average causal effect, which is the thing that we want to do. So if you use this, the assignment to treatment as an instrument, you essentially find the effect for just the compliers. And in general, instrumental variables give you the causal, or the complier average causal effect. There's so many C's here. So the complier average causal effect is what you get out of instrumental variable regression, and that's what you can find. So what we're going to do is walk through a quick example in R that shows you how you can extract the compliers from the always takers and the never takers manually, and how you can do the same thing using instrumental variables regression with assignment to treatment as the instrument. So let's walk through an example now. Okay, so to illustrate how we can find the complier average causal effect, given that we can't actually see who the compliers and the always takers and the never takers are with perfect precision, because there's no way we can read people's minds and see what would happen, what they would do if they were assigned to treatment and if they were assigned to control. As we mentioned in the slides, there's actually a way we can do this. We can find this complier average causal effect if we can find the intent to treat value, which is the effect of being assigned to treatment, not whether or not you did it, if you complied, anything like that. We just have to know if you were assigned to treatment. If we can find the average for people assigned to treatment and the average for people assigned to control, that's going to be your intent to treat value. And if we can somehow use some algebraic trickery to get the proportion of compliers in the population, then we can limit our causal effect, this complier average causal effect, to just the compliers, this pi c here, that were assigned to treatment. And then it's going to be a very limited local treatment effect for just the people who complied who were also assigned to treatment. And that's going to be kind of the most accurate pinpointed causal effect in this experiment. So what we can do is illustrate this with R. And so if you download the course materials for today from the website, or click on the link on the course website to open up the RStudio Cloud project, it should open up a similar RStudio window, but in your browser. You'll notice there are two markdown files here, one called ITT late finished that has all of the finished code in it. All of this code also is on the course website in the annotated example there, so you can also refer to it there. We're going to open up the ITT late empty one, or the original one that doesn't really have much in it. And we'll walk through the code that's here and show you how we can find the intent to treat effect and how we can find this proportion of compliers in the population. So go ahead and open the ITT late markdown file, and we'll run this first chunk that loads the libraries. These should all be familiar to you at this point, tidyverse and Broom especially. Estimator has the IV robust function in it for doing instrumental variables automatically, so you don't have to do the first stage, extract the predicted policy, and then run the second stage. And then if you run this next chunk, this loads some hypothetical data that I created for a randomized controlled trial of bed nets. What the researchers here were doing was to see if using bed nets in this hypothetical village increased health. If we look at the bed nets data, you can see there's just 3 columns. There's the treatment column that shows whether or not the person was assigned to the treatment group or the control group. You have the bed net column that shows if they actually did the program, if they used a bed net or did not use a bed net. And then we have health. which is just this made-up number. I think it ranges from like 0 to 100. The higher the score is, the more healthy you are, is essentially what this is showing. So if you look here, you can see how different people responded to being assigned to the different experimental conditions. So person 1 here was assigned to the control group, and they did not use a bed net. And then they had 24 health points in the end. Given that we know that they were in the control group and they didn't use the bed net, this person could either be a complier, they're actually listening to the treatment and doing, or they're listening to their assignment, they were assigned to control and so they're not going to use the bed net, or they could be never takers, which we can't actually tell if they're a never taker or a complier. If they're a never taker, they would have been assigned to treatment and then not done the bed net. The fact that they didn't do the bed net and were assigned to control, that doesn't tell us if they're a complier. Person 2, same situation here. We don't know if they didn't do the bed net because they were listening or because they are never takers. Person 3 was assigned to the treatment group and used the bed net. But here, again, we can't tell if they used the bed net because they're a complier or because they would have done it anyway and they're an always taker. We have no way of telling the difference there. Person 4, similar. Person 5 was assigned to the control group but used a bed net. And so that tells us that person 5, we know for sure that they're not a complier because they didn't listen to their assignment. Instead, they are an always taker. They did the bed net regardless of treatment. They could theoretically be a defier, where they do the opposite of treatment, but as we talked about in the lecture slides, we can generally assume that the defiers don't exist. We use the monotonicity assumption that says assignment to treatment only increases your probability of actually using the program or doing the treatment. It doesn't decrease it. So we're going to assume that there are no defiers. So person 5, we know for sure they are an always taker. So we could keep going through all 2,000 of these people and try to guess who they are, if they're an always taker, a never taker, a complier. Or we can kind of go a faster route and plot them. But using this bed nets data here, we can't actually tell who is who. And so I also included a second data set here called bednets time machine, which again, you can't see this, but this shows what everybody is. So person 1, we couldn't decide based on this data here if they were a never taker or a complier. Here it tells us they're a never taker. And so in this data set, you can see their health outcomes, what would happen to their health if they don't do the treatment, what would happen to their health if they did do the treatment, what they actually did, and then the outcome. And so these 2 columns, we can't see those in real life. This column we can't see in real life. But we're going to use those columns temporarily just so you can see graphically why compliers are kind of lumped into either the always takers or the never takers, depending on treatment assignment. So to do that, we're going to add a new chunk here, and we're going to make a plot. So we're going to look at the distribution of treatment assignments across these different people here. So we're going to say ggplot. We're going to use this hypothetical time machine data that we can't actually use in real life. So we'll say data equals bednets time machine. And then we'll say mapping AES. So on the x-axis here, we want treatment. And on the y-axis, we want health. So we're going to look at the distribution of all of these outcomes across the different treatment groups. So then we can say geom point, and if we just leave it like this and run it, it's going to look really boring, just a whole bunch of points, which we don't want. There's a lot of overplotting there. We also, because we have this time machine data, we also want to be able to divide these people into what kind of categories they are, if they're a never taker and always taker, and whether or not they used the bed net, and so if they complied or not. So what we can do is add some additional aesthetics here. Inside geom point, we can say AES. We can change the shape of the points. We'll say shape equals bed net. So this is whether or not they did the bed net. And we can color by status. So the status column is this unknown thing that tells us if they're a never taker or a complier, etc. So if we run this now, we should see a whole bunch of colored points. They're all overlapping there. To get rid of some of that overplotting, we can jitter these things. So we can say position equals jitter. So now we should see a whole bunch of strips of dots like this. Hooray. One last thing we can do is, let's get this a little bit bigger. We're going to facet this by status. So that we'll just have a plot for the always takers, just a plot for the compliers, and just a plot for the never takers. So we're going to say facet, wrap, and then tilde status. So if you run this, this will separate the different types of people and what they did and their outcomes. And the nice thing about this plot here is you can actually see, like if you look at the triangles here, all the never takers, regardless of their assignment to treatment, if they're in control or treatment, they're all triangles. They all did the bed net. And they all have higher health outcomes than people who didn't. If we look at the never takers, they never did the bed nets, regardless of their treatment assignment, and they're kind of lower health status here. The compliers, this is where we see the actual causal effect. The control group had lower average health. The treatment group had higher average health. That's one reason why we want to narrow in on just the complier average causal effect, because the always takers, they're different. Like there's something inherently different with them where they care more about their health. The never takers care less about their health or something. There's something systematic with those two groups of people. So we want to limit our analysis to just the compliers. So that's ideally why we want to look at just the compliers. The tricky part, though, is that in real life, we don't see this status here. We just see if they did the bed net or not. So if we copy this code that we just ran for ggplot here, we're going to make a second plot. And we'll use that same code, and we'll only adjust one thing. Instead of wrapping by status, because we can't actually see that, we're going to facet by bed net. And if you run this, this is what we actually see in our data. Again, this is still using the time machine data, so it still does show who the always takers and compliers and never takers are. But if you imagine all of these points being black, then this is what you would actually see in the data. So if you notice in the no bed net section, the people who didn't use the policy or the program, if you look in the control group there's a mix between green and blue points. The green points are the compliers and the blue points are the never takers. We can't actually tell the difference between those two. And so this is what we saw if we looked back at our original data. This person 1, who was in the control group and didn't use the bed net, person 1 is inside here somewhere, and they're a never taker. But person 2 was a complier, and they were in the control group and didn't do it. So person 1 and 2, one is a complier, one is a never taker, but they both look the same here in this mixed up group. You get the same issue with the always takers in the treatment group with the people who actually did the program. This treatment group is mixed up with compliers and always takers. The only groups that aren't mixed up are the control group that used bed nets. We know that they are always takers. They'll always use the bed net regardless of assignment to treatment. And the never takers in the treatment group, if they were assigned to treatment but they didn't use the bed net, because they're never takers, they're never going to do it regardless of what they're assigned to. So those are the only two groups that are like pure. We can actually get there's no entanglements between different groups. We know the exact proportion of people in the population who are always takers in the control group who were assigned to the bed, or who used the bed net, or who didn't use the bed net who were assigned to treatment group. So our goal is we want to do something mathematically to only look at the green points here. But we don't have a column that tells us if they're a complier or not. And so what we see in real life, if we take away this color equals status thing, this is what we see in real life. And so what we want to be able to do is somehow extract the compliers from the control group who didn't use the bednet, and extract the compliers from the treatment group who did use the bednet. And if we can compare their outcomes, that's going to be our complier average causal effect. But that's hard to do. So what we need to do is use the formula that we had here, where the complier average causal effect is this intent to treat effect divided by the proportion of compliers in the population. So we can do this first step, which is finding the intent to treat effect, which is the average outcome for the treatment for people who were assigned the treatment, and the average outcome for people who were assigned to control. So we can do that in a couple different ways. This goes back to what we covered when we talked about randomized controlled trials, how we analyze these things, where you just look at the difference in means between two groups. So we're going to figure out the ITT effect here. We'll just add a comment here. So one way we can do this is by grouping and summarizing. So we can take the bednets data. We're going to group by the treatment column, because we want to see people who were assigned the treatment versus not assigned the treatment. And then we're going to summarize, and we're going to figure out the average health for people who were assigned the treatment and not. So we'll say average health equals mean health. So if you run that, you can see that there is a difference. The treatment group, people who were assigned to treatment, had 46 health points on average, and people who were assigned to control had 40 health points on average. So you could manually say 46.9 minus 40.9, which is 6. Or, like we talked about in the randomized controlled trial session a few weeks ago, you can run a regression model, which will tell you the difference between those two groups. So we'll say ITT model equals LM. So here we want to predict health based on treatment. And our data is bednets. And we want to see the results there, so we'll say tidy ITT model. So if we run that model, the coefficient for this treatment variable is the difference in means. So the intercept there is the average health for people who were not assigned to treatment. And then when you're assigned to treatment, that's the switch that says on average your health is going to be 6 points higher. And if we look back at the results here, the average health for the control group was 40.93. If you look at the regression, the intercept is 40.93. It's the same. And so this is just the increase from being in control to treatment. So our intent to treat effect, the effect of being assigned to be in the treatment group, is this number here, this 5.9877, etc. So we found one part of our formula. For convenience, what we're going to do is just save this 5.98 as just a variable so we can refer to it later, so we don't have to type out 5.9879992, etc. So to do that, we're just going to make a new variable called ITT, and that's going to equal, we're going to run tidy on this model, so tidy ITT model. We're going to filter that data set so that we're only looking at one of the rows. So we're going to say term double equals, so we only care about this treatment coefficient here. So we want term equals that, and then we're going to pull the number from the estimate column. So we're going to pull estimate. So if you run that, you should, if you look over in your environment panel, you should have a new value. It's not a data set, it's just a variable called ITT, and it is this 5.98799, etc. So that is the intent to treat effect, which means we've gotten 1/2 of what we need. So if we look back here, that's our intent to treat effect. So next we need to find the proportion of compliers in the population. And that's where we use some algebraic trickery. If you remember from the lecture, we want to find this proportion of compliers. And we want to find the proportion of compliers here. But they're kind of entangled with proportion of never takers, or the proportion of always takers. So if we say here, this proportion of always takers and compliers is really just the percent of people who are in this treatment group and who did it. If we rearrange these terms here, if we move this proportion of always takers to this side and subtract it, then that leaves us with the proportion of compliers. So it is the proportion of people who were in the treatment group and did it, minus whatever this proportion of always takers is. But if we look at our magic table here, there is a way that we can find this proportion of always takers, and it is over here. The people who were assigned to control, who still did the program, they are our always takers. And so if we assume that they're kind of randomly distributed, equally distributed across both of these groups, in the treatment group and the control group, then we can say that the proportion of always takers in the treatment group is going to be the same as it is in the control group here. And so if we can find this value here, proportion of always takers, then we can actually get rid of this. We have the proportion of always takers here, and we're left with just the proportion of compliers. So this is what we need to find. We need to find the percent of people who were in the treatment group and did it, and the percent of people who were in the control group and did it. So again, this is from the slides here. We found the intent to treat. What we need to do now is find this proportion of compliers. So it's the percent of yes in treatment minus the percent of yes in control. And that we can get with our data. We don't have to read anybody's minds for that. We can see how many people did the program and were assigned to the treatment group and assigned to the control group. So to do that, we'll add a new chunk here. So the easiest way to do this is, again, to use group by and summarize. So we're going to take our BedNets data set, and we're going to group by treatment, but we're also going to group by whether or not they use the BedNets. So we're going to, let's look at the column name. It's called treatment and BedNet. So we're going to group by both of these columns here. So treatment and bed_net. And we want to find the count, how many people there are in each of these groups that are in the treatment group who did it, in the treatment group who didn't do it, in the control group who did it, and in the control group who didn't do it. So to do that, we'll use summarize, and we'll make a new variable called count, and that's just going to be the number of rows in each of those groups. And so if we run this model, it'll actually, oh, you have to spell it correctly, not treatment, it's treatment. Run it. There we go. So we can see here that there were 808 people in the control group who didn't use the BedNet. There were almost 200 in the control group who did use the BedNet. These are our always takers. And then we have 400 people in the treatment group who didn't use the BedNet. Those are our never takers. And we have 600 people who are in the treatment group who used the BedNet. And this is a mix of our compliers and our always takers. So we have counts. What we want to do is get the proportion. And so we need to divide each of these counts by the sum. So what we can do is inside or outside of summarize, we can add another pipe, and we'll make a new column with mutate, and we're going to say mutate proportion equals, so we're going to take this count column divided by the sum of the count column. There we go. So this tells us the proportion inside the treatment group and inside the control group here of people who did the BedNet and did not do the BedNet. So 80% of people assigned to control did not do the BedNet. And again, those are both compliers and never takers. And 19% were assigned to treatment or assigned to control and did do the BedNet. And those are our always takers. So if we look back at the slides, what we care about is the percent of people who did it, who were assigned to treatment, minus percent who did it in control. So we can actually figure that out here. We can either use filter and pull to get those exact numbers out, but because we have to do it twice, we'll just copy and paste here. So we're going to say proportion of compliers equals, so this was, again, the percent yes in treatment. So that would be percent using BedNet in treatment. So that's our 61% here. So if we just copy that and paste it here, minus percent yes in control. So if we come back here and we say, here's the yes, they used BedNet in control. Here's our 19%. So that right there, if we run it, is 41%. So that is the proportion of compliers in our data set. It's not super exact. We don't know if that's perfect, but it's kind of the best estimate given that we can't read people's minds. So if we look back at this original picture here, what we're saying is that 40% of our 2,000 rows, 41% of our 2,000 rows are these compliers here. And so the remaining 60% are the always takers and the never takers. And so we're just going to look at 40% of our data, and they are the compliers here. We're hoping they're the compliers. Okay, so we have, if we go back to the slides, we have both parts now. We have the intent to treat effect, and we have the proportion of compliers. And so if we divide intent to treat by proportion of compliers, we should get this complier average causal effect. So if we add a new chunk here, we can do that. We can say ITT divided by prop compliers. And if we run it, this says that the causal effect is 14 health points. Before, when we just looked at the intent to treat, just whether or not you were assigned to treatment or control, where was that? The intent to treat was 6. That's a lot smaller because that's including the always takers and the never takers. By doing this weird math and looking and dividing the intent to treat by the proportion of compliers, that lets us limit that causal effect to just the compliers, and it's actually a higher causal effect now, it's 14.42. And this is arguably more accurate. One thing we can do, because we have this time machine data, is we can see what the actual causal effect is for the compliers. So let's add a new chunk here. We'll make a new data set called, or we'll not do that. We'll just say BedNet time machine. We're going to only look at the compliers. So we'll say filter status equals complier. So we're getting rid of all of the always takers and the never takers. And then we want to see what the causal effect is. So we can say summarize. So our treatment effect is the average of, and because we have this time machine, we can see what their health would have been had they done it, minus what their health would have been if they hadn't done it. And so we know the hypothetical causal effect if we had a time machine there. So if we say mean of health 1 minus health 0, this is going to be the true causal effect for just the compliers, assuming we have a time machine. And if we run that, the true causal effect, the treatment effect, is going to be 15.5, which is slightly higher than the 14, but 14 is fairly close to 15 there, a lot closer than 5 or 6 is what we had with the intent to treat effect. And so this is arguably way more accurate. Given that we don't have a time machine, we can't actually get this 15 number. That's pretty close, and that's exciting. Okay, so the last thing I want to show is the shortcut to doing all of this. And the reason we're talking about these compliers and never takers and always takers with instrumental variables. And why we care about instrumental variables when we talk about randomized controlled trials. If you remember from the Reading in the World Bank book, it didn't really talk about regular instruments. It didn't talk about father's education or Scrabble scores or any of those kind of standard econometricians' famous instruments. Instead, it talked about using instruments as part of a randomized controlled trial, either to send encouragement and help people use the program more to boost compliance, or as a way of focusing your results on just the compliers and getting the complier average causal effect instead of the general intent to treat effect. And so the way you do that is you use an instrument. And in this case, the instrument we use is assignment to treatment. The nice thing about that is it actually meets all of the requirements of a good instrument. It is relevant. If we look at our data set here, being assigned to treatment has an effect on health. We saw that already with the intent to treat effect. People who were assigned to treatment had 6 health points higher on average. And so that shows that there's kind of a relevant relationship between assignment to treatment and health. The exclusion story says that the only way that you can go from being assigned to treatment and having improved health is through the bed net. And that's our exclusion story. And that seems pretty plausible. Being assigned to a treatment group isn't going to make you do something else, which then increases your health in theory. In theory, like the only way you're going to become healthier because of treatments, because of being assigned to treatment, is because you actually do the program. And so that kind of meets the exclusion principle. And then the exogenous side, there's nothing else in the DAG feeding into assignment to treatment. That is an external thing that researchers decide to do, and so it's an exogenous instrument. So it meets all 3 of the requirements for a good instrument. So given that, we can use IV robust. We could go through all of the manual stages, but that's tedious. We're not going to do that. So instead, we'll use IV robust to figure out the effect of using a bed net on health, and we'll use treatment as an instrument. So we're going to say model, what are we going to name it? We'll call it model IV for instrumental variables. So this is going to be IV underscore robust. Spell it correctly. So our outcome is health. So health is explained by bed net. So if we just ran that regression right there, that's going to include all of the always takers and the never takers and the compliers. And we don't want that. We want it limited to just the compliers. So we need to add an instrument. And the way you do that with IV robust is you use the up and down pipe sign that's above your enter key. And this is where we put the first stage stuff. And so we want treatment. And that's all we're going to do. And then we have to say data equals bed nets. And then we're going to use tidy to look at the results. We'll say tidy model IV. So if you run this here, you should get an effect of 14.4, which coincidentally, or not coincidentally, if you scroll up, this 14.42, it's the same as doing it by hand and finding the intent to treat effect and dividing it by the proportion of compliers. By using an instrument, that is inherently what is happening all by itself. And so you don't technically need to go through the whole process of looking at this magic table and rearranging things to make sure that the right proportions are on the right side. By using an instrument, that happens by itself. That's inherent in the math of using instruments. And the other advantage of using an instrumental variable approach instead of doing it by hand is you get significance measures and you get standard errors. And so here, all you're getting is this number. There's lots of complicated math you can do to get the standard errors for that, but you don't need to worry about that because IV Robust will do that for you. And so you get standard errors, you get significance, and so you find that for the compliers, the complier average causal effect using a bed net has a significant causal effect on health. It causes you to have 14.4 points higher health on average, and that increase is statistically significant. That is with the caveat that it only applies to the compliers. It doesn't apply to people who would have done bed nets anyway or people who wouldn't have done bed nets anyway. It's just for people who obeyed their assignment to treatment. But as long as you stick with that caveat and say that it is a localized effect, not a general population level effect, you can talk about causation legally. And you can say that this randomized control trial had a positive effect on the segment of the population that it was targeting. And so that's how you can use R to figure out all of these different moving parts and more simply just use instrumental variables with this assignment to treatment as your instrument to get that same complier average causal effect. And so that's how you do it.